in how it actually operates for plants. And then for the chemical properties, they can have different nutrients and minerals that are in that soil, whether it has a lot of calcium or not very much calcium, or nutritionally, if there's a lot of nitrogen or phosphorus in the soil, they can differ in that way. And also, one of the things that I do a lot in my work is how the pH, or whether that's an acidic soil or a basic soil. We have a lot of basic soils around here, meaning their pH is higher than 7. And in a lot of other places where the soils are older, they have a lot more acidic soils. But we have young soils here. We have calcareous soils, and a lot of those are basic or high pH. Or salinity simply refers to whether it has salts in that or not. Biologically, this is a whole interesting section of soil that we've known exists, but hasn't been talked about, haven't been really well understood, how impactful that biological community of the soil is. And so you can have, there's a whole host of organisms that are in the soil. Macrobes, that just refers to big organisms like worms or nematodes, or small organisms, or the really, really small microscopic organism. And those are actually the ones that play the biggest role in soil. And it's actually said that if you have like just a little handful of healthy soil, there are more organisms in that soil than there are people on Earth. So there's a lot going on in that soil, in that biological section. And this relates to it, but I just wanted to put it on here with this organic matter, and that just, it simply refers to anything that is carbon-based that's in that soil. Anything that came from or is a living plant or animal, a carbon-based compound. That's where we get our organic matter. And that forms the lifeblood of this biological community, that carbon in the soil, that organic matter, is very critical. But let's talk a little bit more about this soil texture, because that's one of the very basic things that soil has, that we use to classify it and how a soil behaves. And I have here 3 items just to help us understand a little bit more about how much give you an envision of how texture is in it. We have a sand particle, a clay particle, and a silt particle. And this basketball I have here, that is a very, this represents a sand particle. And then comparatively in size, you have this golf ball would be a silt soil particle. So obviously that's much bigger, but just proportionally, that's about more what you're looking at. And then for clay particle, that's sort of like a little tiny, like a little BB you'd shoot out of a BB gun. So compare that to a clay particle or to a sand particle. And there's very different sizes. So you have sand, silt, and clay. And why does that matter? Why do we care whether we have a big soil particle or a small soil particle? And the answer to that is because it matters. It changes how a soil behaves. And so let's just talk for a second about texture and how soil texture impacts how plants are able to, what plants grow in that soil and how plants are able to utilize that soil. Remember that medium that they're having to grow in. And when we're referring to the sand, silt, and clay, we're specifically referring to that mineral component of the soil. So the size of those broken down rocks we refer to as parent material. When they get broken down and they get smaller than the gravel particle size, you get into the sand particle size, or the silt particle size, or the clay particle size, as it's really tiny. So just the factors that are affecting how plants operate on a rangeland situation. We have how texture influences soil. And then I'm going to have a little bit of a demonstration here in a minute about why this matters. But first of all, soil texture affects how water drains through a soil. And related to that, water holding capacity. A soil, if it can hold a lot of water or a little bit of water, you can see how that would affect how a plant would grow in that soil. And also, believe it or not, there is actually a large component of soil, depending on the soil that is there, that is air. You have water, air, mineral soil, and the biological community in a soil. And so that aeration is affected by the texture. Also, erosion potential, because if you can imagine, if you have a sandy soil or a clay soil, they would be affected differently by water erosion or wind erosion. Or if you were working on a rangeland project and you had more of a sandy soil or a clay soil, once that soil was broken up, the clay soil could potentially be more impacted by wind erosion or water erosion than a sandy soil, for example. But given the situation, they could both erode considerably. The organic matter content, that affects how the soil behaves, and it's affected by what plants are growing there, which the soil texture influences. pH and changes to pH are actually affected by soil texture. Sandy soils tend to be lower pH or more acidic, and they tend to have less buffering capacity, meaning they can't resist changes in pH as easily as compared to a clay soil, which we won't get into it much, but that's also related to the cation exchange capacity. It just refers to the chemical reactions that go on in the soil, and cations are the minerals that are broken down from the parent material that are important to plants. And if you, for example, have a clay soil, that is, you have more cations being held by that clay soil, or potential to be held by that clay soil, than in a sandy soil, for example. And then the last one I'm referring to is soil tilt is affected by your texture, which this more or less refers to. It can refer to the tillage potential of the soil, but it also refers to just how a seed is able to germinate once it is placed into the soil. The texture can affect if the soil surface crusts, for example, or related to the water holding capacity, or if it's compacted. That's all related to that soil tilt. So with soil tilt, just think ability, or what the situation the seed is in when it's getting ready to germinate. Okay, and so now that we're talking about that, let's just hear just a little bit. So what soil is the best soil? And I have, because you can have a sandy soil, you can have a clay soil, or you can have a silt soil. And which one is the best is really the question. So you can have clay, silt, or sand. And which one is the best is always the question. Do you want a sandy soil that allows the water to infiltrate, but it doesn't hold on to that water as readily? Or do you want a clay soil that has better cation exchange capacity, but and it holds on to moisture better, but it's really difficult for the moisture to get in, has a tendency to be compacted. There's trade-offs with all of that. And so really the answer is if you had all these choices, the answer would be about right there. Somewhere in the middle is what you actually do want. And so you're going to be, you can look on the internet and find what's called a soil triangle all over, and they use it they classify a soil based on texture. And that soil triangle just simply is referring to if you have increased clay percentage, goes up. If you have increased silt percentage, goes that way. And if you have increased sand percentage, it goes this way. And right here in the middle, it's not exactly like this, but right there in the middle, it's referred to as a loam soil. And that's more or less an even mix of sand, silt, and clay is a loam soil. But then you can have a sandy loam soil or a silt loam or a silty clay loam. There's all sorts, and they have little, but let's just say this is the 50% line, 50% line, 50% line. If you follow those together, that's more or less where you get into the loam soil. And they classify soils based just on that soil particle size. And I have a little bit of a demonstration here that just is why this is such a big deal to a soil scientist. So, if I can get this just right here. I have 3 jars here, and this one here is filled with lima beans. This one here is filled with rice. And then this one here, I wish it was another light colored, but it's what I had was chia seeds. So chia seeds represent clay soil particles, rice representing silt soil particles, and then lima beans, because they're much bigger, representing a sand soil particle. And then we have here, so where I'm going to show how water would infiltrate into this soil profile we have here. Just refers to what this, if you're just looking, this is the soil surface right here on top, and we're just going to see how the water flows down through this soil profile. But because we're on a microscopic scale, this drinking water, just this plain water, isn't going to behave exactly like we'd be able to show in this visualization if I could switch and use corn syrup. And I put some red food coloring in this just so for visualization purposes. But I'm using corn syrup because it's a little bit thicker than water. In fact, I've added a little bit of water to get the texture or the consistency about right. But water has things called hydrogen bonds, which means they, on the more of a molecular level, it's sticky, sticks to itself, which matters in the soil. It actually, the water, it is held around the outside of each individual soil particle. And so just to help us visualize that, I'm using a corn syrup so that it's a little bit more sticky and thicker on a molecular level, which we're trying to visualize, like we're looking at this through a microscope. And so I am just going to pour some of this on the top, and I'm going to start on the sandy side and then move from there to the silt, or the clay side, moving from there to the silt to the sandy soil, because we know that a sandy soil has a faster infiltration rate than a clay soil. So I'm just going to show this visualization, and we're going to watch what happens. Okay, so as you can see, it's working its way slowly down through the silty soil, but on the sandy soil, it moves rapidly down through there. And then on the clay soil, it's working its way, but it's slow because of those. There's not as much pore space for that to infiltrate down into, as well as those hydrogen bonds would be kind of holding, slowing the movement of that water down through the soil profile. Surface tension is the same thing. It's a result of those hydrogen bonds. And if this continued, like soil doesn't have a bottom to it, or at least you don't want it to have a bottom to it. And so water will just filter through the soil and go out the bottom. This isn't shown in this demonstration, but as you can see, you know, if we had a sandy soil, that water would have just disappeared right down through that soil profile, and very little would have been stuck around each of those individual, you know, in the pore spaces and sticking around the outside of those soil particles. Silt is just in the middle, but you can see the clay, once the water gets into it, it holds on to it much more readily. So in a rangeland situation, this affects what kind of plants can grow there to a great degree, is influenced by soil texture. Oftentimes, if it's a high pH, it affects what types of plants can grow there. If you're doing a restoration project, what impact there might be to if you're doing a project where you're removing woody vegetation like sagebrush or juniper trees, you know, the potential for erosion would be affected by this. And so soil texture and soils, that's really at the root of a lot of things that are going on out there in the rangeland. And so I'm just going to have, if we can, get my contact information put on a slide here at the end of this presentation. And if you have any questions, you're welcome to contact me. But we're going to be utilizing this information on soil texture in our Rangeland Skill-A-Thon coming up here in a few weeks. Thank you.
Okay, thank you, Bracken. I'm going to hit